know you're here.
Yeah. You're not like an imposter or something. Yeah.
If we want to get money so the CTF Club can do more Jolly Ranchers.
Jolly Ranchers?
All right, let's get started. So, talk about greedy algorithms. So, what are greedy algorithms? So, a greedy algorithm is an algorithm where you can break down a larger problem into smaller subproblems, and then for each subproblem, pick a locally optimal solution, which will hopefully give you the answer to the global problem, right? So, it's not a guarantee that it is going to be the solution, but this is a simple way that a lot of problems can be solved. So when can we use them? So problems that can be solved by making local decisions without needing to backtrack really are optimal for greedy algorithms. And this one's a little more abstract, but basically when you can take something and break it into nice subproblems, if there's not really a better way of saying it without demonstrating it, which I'll do later, but if there's a way to break the problem down into smaller problems without breaking anything with the overall problem, and then being able to solve each of those little ones is the big idea. So for example, if you have a bunch of intervals and you need to schedule things along in time, you can use a greedy algorithm in general for that. I'll show one of those later. Coin changing, depending on the implementation of that, you can use greedy algorithms. And Dijkstra's shortest path actually uses a greedy algorithm. I talked about that last week, but it chooses a locally optimal solution at each node, which ends up giving you some extra information. So I have a little framework here that I wrote up for how you can solve a greedy algorithm problem. So first, what you need to do is identify what the locally optimal choice is. So it's not necessarily always very obvious. Like it's not just like choose the biggest number here. Sometimes it's a little more nuanced than that. You have to figure out what the actual problem is asking and then divide that into the sum problems and choose what the locally optimal solution at each subproblem is. And the second thing I have here is to ensure the choice is indeed locally suboptimal or locally optimal and safe to perform, meaning that choosing the option at the subproblem won't ruin the entire rest of the solution. Again, that takes a little bit of working, and I'll explain that later exactly when you can kind of determine whether or not a greedy algorithm is going to be sufficient. And then another thing you want to do is to ensure that the smaller problems, the way that you've chosen to break them down, can actually be solved in the same way, like you can generalize them. Because if I break something down into 10 different subproblems, but each of those subproblems requires a different solution to solve, that's not really a good breakdown into subproblems. I need something that's general, so I can just iterate over all the subproblems and do one operation on each of them and get the answer. And then the fourth step is just going to be to implement the solution. Like I said, iterate over the subproblems and solve them. So for example, I have an interval scheduling problem description up here. So if you're given a list of intervals, you need to find the maximum number of non-overlapping intervals. So what that means is if I'm being given an interval, say 1 to 3, and then I'm given 3 to 4, and I'm given 4 to 5, I know that I can fit all three of those in because they're not overlapping. They meet one right after the other. But if I'm given 1 to 3, then 2 to 4, and then 4 to 5, only two of those can fit in, the 1 to 3 and then the 4 to 5, because you don't want the 2 to 3 to overlap anything, right? And I have, with the greedy choice, we know that basically there's not really a way to guarantee that the greedy choice is the right outcome, but based on the problem, the wording of the problem, you can kind of guess that this is going to be something pretty simple. And yeah, so you just have to ensure that you're not going to ruin the overall problem just by doing a locally optimal choice. I have some code that I'll show up here. Don't worry if this isn't immediately obvious. I have some examples I'm going to go over where I'll code it like in front of you to show you exactly the thought process that I go through to solve these types of problems. But I do have a couple examples of this specific problem in code. So here it is in Python. So what I do, the dot sort method, if you can't guess, it sorts something that you give it. So in this case, I define the key to be sorting by the second value, so the first index, but we're indexed at 0. So the second value inside of each interval, because the way the intervals are in there, it would be like 0 to 3, and I want to sort it by the last element of the interval rather than the first. And because in that way, I can guarantee that I'm not going to have overlapping, right? And then I just keep adding them in there as long as the start of the new one doesn't overlap the end of the last one. Similar in C++, the exact same process, just more annoying to write and look at. So here is where I'm going to do an example problem on Caddis. So we'll read through the problem description together, and we will, I'll code it in front of you. So I will do a new tab here, and the problem is called planting trees. So I'll name it planting trees. Actually, I'll call it. So I'm going to write it in Python because that's where I'm most comfortable. You can write it in pretty much anything. I'll pull up the problem. So just look at the problem description. Farmer John has recently bought N tree seedlings, so N is the number of seedlings, and he wants to plant them in his yard. So John's a lazy guy, so it takes an entire day for him to plant one seedling, and for each tree, he knows exactly how long it will take for that tree to grow to full maturity from the moment he plants it. And also, he wants to throw a party after the last tree is matured for all of his friends because he wants to show off his cool trees. So, more precisely, the party is on the earliest day, or earliest on the next day after the last tree has fully grown up. So we need to find an optimal way of placing all of these trees given how long they take to mature and ensure that it takes the fewest number of days from now until he throws his party, right? So does everybody understand what the problem is asking for here? We're being given the number of trees, and then we're being given how long each tree takes to mature. So this tree takes 2 days to mature, this tree takes 3, this tree takes 4, this tree takes 3. Does that make sense? Dish. You can plant one a day. So you have to choose which one gets planted on which day, right? So this type of problem, the reason that you can tell that it's going to be a greedy algorithm problem is because it seems pretty simple, right? That's not like a surefire way to tell that this is definitely a greedy algorithm, but just reading it, most of you can probably come up with in your head a way that you would do it on paper, right? Like place the biggest tree first, the one that takes the longest because you want to get that one out of the way, and then from there place the ones that take less long, right? That's a pretty easy way to approach it, and that actually lends itself nicely to a greedy algorithm approach. A greedy algorithm is what you just did in your head, where you choose the best solution for each day, and the best solution for each day happens to be the one that will take the longest that you haven't planted yet. So what we're going to do is write a solution to this.
Josh, your screen share is broken.
How?
It's not going through Discord.
Okay. Let me try doing it.
If you make sure you click screens. Yeah.
Okay.
Okay.
Did that work?
Good. Yeah.
Okay. So back to this. One thing we're going to want to take a look at is how the input is being given to us. We're being given n, which is how many trees there are. So we're going to want to read that in. The way you do that in Python is by reading it in with the input command, or not command, function, which allows you to type in a number, and then it'll return that back to here. And then I'm going to turn that into an integer using the int, and then put the parentheses around what I want to turn into an integer. So now I don't have to worry. I just know that n is how many. Is there a way to turn this? I guess I don't think there is. Okay. Just try to ignore that, I guess. My IntelliSense is going crazy. So now what we've read in is this first number. Next, what we're going to want to do is read in all these next numbers. And the way in Python that I tend to do that, when I have an entire line just one line full of a bunch of numbers. I don't really care how many there are. In this case, we know there's n, but that doesn't actually matter for this. So I'm just going to read in the trees to be converting to a list, and the map function returns an iterator. And then I turn that iterator into a list. So what I'm doing here is I'm taking the input and splitting it. And by default, the dot split method splits on spaces. And then for each of those, I'm mapping each element in this input.split into an integer. So I'll actually demonstrate what that looks like. So first what I'm going to do is just demonstrate what it would look like if I do it like this. So I'll run this code, type in 4, and type in 2, 3, 4, 3, our input. And as you can see, by default, when I just read it in with a split, it splits them all at the spaces and read them in as strings, but we don't want that. And there is a way to just loop through the entire trees array, or list in this case, and convert them all to an integer. That would be like this. Like IntelliSense so easily gives me. But this is 2 lines, and I only want to write 1, so I'm going to use the map command, which does the exact same thing. So the map function takes in the type that you want to convert it to, and then it takes in what the iterator that you want to convert. So what map the function does, it goes to this iterator, loops through the entire thing, converts each of them to this type. So if I wanted them to be floats, I could just do that, right? But I want them to be integers because that's all I need to do. And this, by default, will return an iterator. So if I try to just do it like this and print the trees, okay. It's going to return a map object, which is a generator, and I do not want that. I want it to be a list that I can repeatedly work with. So I'm going to convert that to a list. Using the list and then putting the item in the parentheses that I want to convert is how I do that. That's how you cast something to a different type. So now that we've read that in, the next step is we want to sort the list based on the ending of each interval, right? So this is going to be an interesting line of Python, but it's actually not that hard. So what you're going to do, I'll call it trees sort, and I want to sort it by reverse, right? Because by default it sorts in ascending order, but I want descending order, meaning it's going to start with the biggest, then the next biggest, then the next biggest. So by providing this reverse equals true inside of this dot sort method, it will sort it in reverse order, which is exactly what I want. So now, if I run this, and I'm going to print out my trees, now what it looks like, it takes these numbers and then sorts them in reverse order. So it starts the biggest, then the next one, then the next one, then the next one. Pretty simple, right? So now that we have that, what we want to do is initialize a variable to be the latest maturity day, right? So I'm going to call it latest maturity day, which is going to represent the latest possible day that he can have his party, right? So I'm going to start that at 0 because so far we haven't actually done anything. We want to loop through. Then I'm going to loop through so that little line uses the enumerate function, and I'll actually show you what it looks like when I call enumerate. So if I just print enumerate trees what it's going to do. Wait, I want to print a list of it. I'll actually just print it in the loop down here just so it's easier to see. Just to show you what the enumerate function actually does. So what it does is it enumerates it, meaning it counts them. So first it's going to take, starting at this value, it's going to take this element and the element from the iterator I gave it, which is trees, and assign it. So right now our trees looks like 4, 3, 3, 2 because we've sorted it. So it's going to assign 4 to 1, 2 to 3, 3 and 3, 4 to 2. So you can think of it as this is the index. That's one indexed. This is the index for the second one. This is the index for the third one, the fourth one, right? So what that's going to allow us to do is a quick way of determining which day we're on, because we're not really starting at day 0, we're technically starting at day 1, right? So what we're going to want to do next is calculate the maturity day. So the current maturity day at this step of the greedy algorithm is going to be equal to the current day that we're at plus the growth time that we're at. So first what it's going to do, it's going to do 1 plus 4, right? Because if you plant the one that takes 4 days to grow at day 1, then the maturity day that it will reach is day 5. It takes until day 5 for it to reach its full maturity. Then what we can do is just compare it to the figure that or the variable that we designed or assigned before, and compare it and see if it's bigger than that variable. So another way of writing this line is to do something like this, where instead of just doing it like that, I can just do if maturity day is greater than the latest maturity, meaning that if the current day that we're at, if this 1 plus 4 or this 2 plus 3 is greater than the maximum maturity day we found, then I can assign the new maximum maturity day to the one that we found. So that's just like this is a little simpler way of writing that, but I'll keep it this way. It'll do the exact same thing. Then what we want to do is at the end of here, we want to print the day of the latest maturity plus 1, right? Because for that extra day that he has to wait before he can have the party, because it matures on the 6th day, say, and then his party happens on the 7th. So this will print out the answer to what to the question. So just to go over again what we did is take all of the maturity lengths, the time it takes for a tree to reach maturity, then sorted it in reverse order. So we can place the tree that takes the longest to grow on the first day, and then the second longest on the second day, and so on and so forth. Then in this loop, we've calculated, given that I plant a tree that takes X amount of days to mature on day whatever, I can calculate what day it will mature on by calculating the day that we're on plus how long it takes to mature. So say the current maturity day the current day we're on is day 4, and it takes 5 days for the tree to mature. I know that on the 9th day, that's how long, or that's when the tree will fully mature. So this latest maturity is we're keeping track of which tree is going to extend the time the farthest, right? So in this case, without actually running this and printing it out, we can figure out what it does. So what it's going to do, it's going to loop over these values here. So first, it's going to calculate 5. 5 is bigger than our current 0, so it's going to assign the latest maturity to be 5. Then it's going to go to the next one here. 2 plus 3 is also 5. It's not greater, so it's just going to keep that at 5. Then it's going to go to this one. 3 plus 3 is 6. So meaning that we planted a tree that takes 3 days to mature on day 3. So that means that it won't mature until day 6. We're keeping track of the longest, the one that will mature at the latest date. And then what it does is it loops through this next one. It finds that that is also equal to 6, but latest maturity is already 6, so the latest day that it could possibly be is 6. Then what we're going to do is, because the last tree matures on day 6, John, our farmer, can have his party on day 7. So that's what this output is here. If we run it, we should get the exact same output. Print it? Yes, exactly, 7. So that's for that test case. We probably better do the same thing for this test case just to make sure that we didn't mess anything up. And it happens to print out 42. That is the correct answer. Does everybody see like how that process works, right? Does it make sense?
So you pre-calculate each maturity day, and then just kind of traverse and see.
Yeah, you find the latest possible day that any of the trees are going to mature on, right? And the actual greedy part of this algorithm is the fact that we sorted it in reverse order. So picking the best option is the tree that takes the longest. So we pick the tree that takes the longest at the earliest date, and then the tree that takes the next longest at the next earliest date, right? So that's what this reversing in sorting in reverse order does. Is that's our greedy step. That's our choosing the locally optimal solution, in which our locally optimal solution is which tree takes the longest, because we want to get those out of the way first. So I'm sure that if I were to give a list of these numbers to you, you could do the exact same process. Like if I told you, I need you to figure out what the latest day or the earliest day he can have his party on. I'm sure you could figure it out with this process of, okay, I'm on day 1. I want to get the big ones out of the way first. I'm going to put the one that takes the longest. Then for the next day, I'm going to put the one that takes the next longest. And that's exactly what our implementation has done. This is what our Python code has done, is it chooses the best option at each choice, which tends to be the most intuitive thing for us to think about, right? Greedy algorithms tend to be the immediate obvious solution, which is why they work for problems like this. Like if we look at the difficulty rating on this problem in the metadata, this is a 1.6 difficulty. This is a very easy question on Caddis, but obviously you don't see how difficult the questions are in the competition, but you can kind of get a hint based on the wording that this isn't going to be a very hard question, because you can probably figure out all of these by hand if you want. So this is exactly what I would do if I wanted to figure it out by hand. So this is how we implemented it in code. And if we want to see if it'll work, we just have to press start coding, copy our code, put it there, and submit it and see if it works. It's going to run it on the 2 test cases that we submitted, and it's going to run it on a bunch of extra secret test cases that we're not allowed to see. And in this case, the judgment was accepted because all of the test cases passed. So that's for that question. Does anybody have any questions about this this problem on Caddis or about greedy algorithms? Because I have another example I can go over. No questions? All right, let's go on for another example. This one's going to be a little more complicated, but in the same vein as choosing, like I said, greedy algorithms choose the best option at each state. So we know that one works. So we're going to go back to here. Our second one is going to be a problem called bank Q. Let's open that up and let's take a look at it. This one has a little bit longer of a description, but we'll go over it here. So Oliver is a manager of a bank near KTH and wants to close soon. I'm not sure what KTH is, but it doesn't really matter for this question. There are many people standing in the queue waiting to put their cash into their accounts after they heard that the bank increased the interest rates by 42%. Again, this doesn't really matter for the question. They often toss in a lot of extra information just to confuse you. These numbers do not matter for this question. It will not affect the question at all. However, there are too many people and only one counter is open, which can serve one person per minute. Greedy, hint hint at what algorithm you're going to be using. Greedy as Oliver is, he would like to select some people in the queue so that the total amount of cash stored by these people is as big as possible, and that money then can work for the bank overnight. There is a problem though. Some people don't have time to wait until the bank closes because they have somewhere else to be. So they have to be served before a certain time. and after which they just leave, right? So Oliver, this is just ensuring this last sentence here. Oliver also turned off the infrared door sensor outside the bank. This just means that you don't have to worry about them adding any more people into your queue. You just have the queue at the beginning and you can just deal with that. You don't have to worry about extra customers coming in. So the task is to help Oliver calculate how much cash he can get from the people that are currently in the building. So this is what our input looks like, but just to go over the actual problem, does anybody have any ideas of like how we could approach this problem? You don't have to phrase it in the way of like how I would code it. Just go over like if you were to try to solve this on paper, how would you do it? Any suggestions on that front?
Something to do with like a special sort, kind of. Like kind of the other one we did.
Yep. One of the key things about greedy algorithms is you tend to do a lot of sorting. Well, not a lot of it, but you generally do it at the beginning. So, like you said, a special sort. What do you mean by that?
Well, because I know sometimes you have to put a special key in there because we have two things. It's not just money amount. We have to also consider time.
Yep, we have to worry about
if someone's a
time,
big thing, but they have to do later on, then we might lose out on people who wait longer and stuff like that. So you might need a special key sort.
Sure.
I'm not sure how to go about it.
So, what I'm thinking is first, we can for sure just order by how much money they have. Then from there, we have to worry about what their time is, right? So for this, in this case, person one has $1,000, this person has $1,000, and they need to leave by time 1. So actually, I'll just go over this input again. It gives you N and T. N and T are the number of people and how long it takes for him to, how long until he's closing the bank, like how many minutes, right? Then after that, there are N lines where you have 2 integers. The first integer is how much cash they have. The second integer is at what time they need to leave, right? So we just want to make sure, like this person, he has to leave by minute 1. So we have to ensure that either we serve him if he has a lot of money, or we don't if he doesn't. So this person here, he needs to leave by minute 1 and he has $1,000. This person needs to leave by minute 2 and they have $2,000. This person needs to leave by minute 2 and they have 500. And this person needs to leave by minute 0. They need to be the first person, essentially. If we're going to use them, they need to be the first person we use. And this person needs to leave, or this person has $1,200. So if you were to try to solve this, just looking at this, what do you think you would do first? Well, just actually not like sorting it. Like just if you're looking at these 4 numbers, what would you do, like on paper as writing it out? Who would you choose first and why?
Let's say this person has to go now, this person has to go up to 1 minute.
Okay.
These people have to go up to 4 minutes.
Okay.
Then I would sort those groups.
You could do that, yeah. Okay. That's a good approach. An easier way to do that, like so in your approach, who goes first?
The person 100,
Yes, and why?
they have to go now because their time is 0.
Yep, they have to go now. So if we're going to use them, they have to go now. So that 1,200 is the first person to go. Then next, who are you going to use?
The person with $1,000
And why is that?
because they have to go next.
They have to go at minute 1. Yep. Then after that, who are you going to use? You have 2 choices here. You can do either this person or this person. So who are you going to choose?
I would put more money
Yep. And why is that?
because it would be more profitable because we're trying to fit as much money as we can.
That's exactly right. So the problem description asks us to calculate the maximum amount of money that you can get from these people. So what we're going to do is take this person at the first slot, take this person at the second slot, and then for the third slot we're going to take this person. And 1,000 plus 2,000 plus 1,200, which are the people that we took, happens to be 4,200, which is the answer. Now here comes the fun part. We have to actually write this in code. So I'll do a new file, call it BankQ. Also going to be doing it in Python. And first what we're going to want to do is read in N and T as they've been given to us. So the way I do that is like this. Similar to how I explained it before, except instead of converting it to a list, you just unpack it into two different values, n and t. It's just a shorthand of reading in different integers, right? Next, what we're going to want to do is read in all of these people. So there's a one-line way to do this, but I'm going to do it in multiple lines because it's a little easier to understand. So for blank in range n, this number, this iterator doesn't really matter. I could call it literally anything I want because I don't care what it is. I just need to do it that many times. And I'm going to initialize a list of people. I'm just going to call it people, and it's going to be empty. Then for each of those, I'm going to have my C and my I, and that's going to be similar to what we did before. For each of these that I'm looping through, they're going to have two different integers. So the C is going to be 1,000, and the I is going to be 1. Then the C is going to be 2,000, the I is going to be 2. Then we're going to append exactly like my IntelliSense wants me to do. Append a tuple, which is a data type that's immutable, but we don't need to worry about it being immutable because we're not actually muting it. We're not changing it at all. So now my list of people, I'll actually print out list of people just to illustrate what this is going to look like. And it's exactly as we expected. I actually, it got input in as the, I actually want to do this in the other way, it just makes it a little easier. So what we have here is we've taken a list and we've divided them into pairs. So this first pair is item 1, this second pair is item 2, this third pair is item 3, fourth pair is item 4. And that's exactly what our list looks like. So now we can actually manipulate this list. So what we're going to want to do, I really wish this thing would stop trying to help me, but we're going to want to do, and we want it to be in reverse, and we want to sort, but I'm going to sort by the first value, which is the 0th index in the tuple.
Yeah.
Oh yeah. Good catch. So now if I print out people, it's going to look a little different. It sorted it by this first number. It sorted it by how much money they have, which is exactly what we're concerned about. We want to know how much money they have because we only serve rich people here for some reason.
Thank you.
So now that we have that sorted, what we can do is iterate over that. But first, we're going to want to define some variables. So first, what we're going to want to define is like a list to keep track of which slot is occupied by who, right? So in this case, slot 0 is going to be occupied by this guy. So I'm going to initialize an occupied list to be none times the length, or by how many people we have, or the amount of slots we have, right? So in this case, we have 4 slots to fill. So my occupied is just going to be none, 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 none. It's just going to be 4 empty slots so far. We're also going to want to start off with how much our total cache is, right? Now, here comes the fun part. Here comes that actual iterating over the subproblems part. For, I'm going to call it cache and time limit in our new sorted list. Now that we have this list sorted in reverse order, we just have to start from the latest minute in that list. So like Deshant described, we have like different groups of people, right? Like we have these people that need to go in this time slot, these people that need to go in this time slot. We're going to iterate over all of the times the amount that happen. So in this case, when I'm at index 2, it's going to loop over each of the ones that need to be done in this time, right? Actually, scratch that. What it's going to do is for each of them that cost the same, this isn't a great example because none of these actually cost the same. But if I had another one that was 1,000 and they need to be done by hour 2, for each of these values, it's going to iterate over all of the time values, and it's going to choose the one that needs to happen earliest. Because if I have a guy that's going to pay $2,000 into the bank, that he needs to go in 1 minute, but another guy that has $2,000 in the bank and he doesn't need to go until 5 minutes, I don't need to worry about the 5-minute guy. I need to get this guy done as quick as possible. I need to get the 1 minute guy real quick. So that's what we're going to be doing here. So looping over all the minute. So I guess an easier way to do this is just going to be so I'm sorting it by so the minimum of where we currently are in the list and the maximum time limit, right? So yeah, so time limit is what we're currently at, and T is the maximum time. So I'm just choosing the minimum of those because that's really what matters here. And I'm going to go to the last element, and I'm going to go backwards. So that's what that line does. In Python, if you do -1 for the jump section of the range, it'll do it in reverse order because I want to count from the last and go back. Then an easier way, I'm just going to write it like this so it's more clear. So I'm checking if the current minute that we're checking, we're looping through all the minutes that are possible that are left, right? So if we're at minute 2, it's going to loop through 2, 3, and 4. It doesn't have to worry about stuff that we already chose because that doesn't really matter anymore. So if this minute that we're already at is not occupied, then we set it to be occupied by the current value of cash. And we add to the total cash the current value of cash, and then we break out of the loop. So what this does is it sorts all of the ones that have the same price by how many minutes they have before they need to leave, and then chooses the one that has the least number of minutes. Because like I said earlier, if we have one guy that needs to get out right now and another guy that has the same amount of money and needs to get out in 5 minutes, we're going to choose the guy that needs to get out right now, because if we don't choose him right now, we're not going to be able to choose him later. So that's what this little bit here does. Then all we want to do is at the end of the loop, we want to print the total cash. So what this does is it's iterating over all of the people and their values. It's iterating over how much cash they have and how much time before they need to leave. Then all of the rest of the available minutes, it's going to sort by the closest to the current minute. So if we're at minute 3 and somebody needs to get done at minute 4 and someone else needs to get done at minute 5, it's going to give us that 4-person first and the 5-person next. Then, because we've sorted it by that, we can just choose that the first option is the optimal option, though the one that needs to get done earliest is the optimal option. And we can break out of this loop, which breaks out of this for loop here, not this upper one, just the inner one here, and then goes to the next person. So in this case, we've chosen the best choice, but if somebody else was in that time slot that we're currently at, so at this minute slot, they're kind of just shit out of luck. They don't get to put their money in the bank because we chose somebody with more money. That's essentially what this script does. So if we print the total cash, we're expecting it to be 4,200. I'll run this and see what we get, and hopefully it's right. It is indeed 4,200. So for this one, we'll just go over the approach here and see if we get the same answer that they're getting here. So I'm going to choose this person first, right? Because only one person needs to go at minute 0, and this guy's that guy. So 1,000 is added to our total. Then I have to choose between these two people that get to go at minute 1. I'm going to choose the person that has the most money. I'm going to choose the 2,000 guy. And we already had 1,000 in the bank, and we just added 2,000, and 3,000 is our answer. So I'll run this with our program and see if it gets the same answer. And it indeed does. So next step is to submit it and see if we forgot an edge case or if we actually got it right. Looking good so far. Cool. So the judgment is accepted. That means it got all the test cases right. Yeah, so that's the solution for that. Does anybody have any questions about that? Ish.
I thought an easier way to do it would be, so you have a for loop,
Mhm.
and then you have a, so inside the for loop you say that this list is, so you make a list that's empty, and then you say if the time is equal for some people, then you append them to this list,
Mm-hmm.
and then you append it to the bigger list outside the for loop. And then on the next iteration, the list would be empty again. You keep doing that, and then you have sublist with the same sublist of people with the same time,
Mhm.
and then you can get the max of them,
Yeah.
and then just add all those, and then you.
Yeah, that would absolutely work too. That solution does avoid needing this gross looking line because, well, as your solution, you separate people based on what time they're at. I separate people based on how much money they have. But yeah, either one should work. I think yours is also a similarly accurate greedy algorithm, just implementing it in a different way. If you want to try writing that, that'd be good. But yeah, this is the way that I decided to do it. This is greedy because the locally optimal choice is choosing the person at this time slot that has the most amount of money. And we know it can be generalized because I'm not going to have to worry about the taking the max of numbers is going to be the same every time. It doesn't really matter, right? And yeah, so this is our sorting, and this is our greedy step. Does that make sense to everyone? Cool. All right. I do have some more slides to go over, and then I have a couple extra examples if we still have some time. So like I said earlier, there is a little bit of a caveat with greedy algorithms. They are not always the optimal solution. As you could see by our implementations, most of them were like 10 to 15 lines, pretty simple, and it was fairly immediately obvious what the answer was going to be, right? You could do it by hand, which generally these problems, if you can do them by hand, a greedy algorithm is going to work. But it's not always going to work because sometimes there's a little more nuance involved, or a just greedy algorithm is just not the right approach because you have to worry about affecting the global problem instead of just affecting the little problem. So I have an example up here for currency systems that does not work. So there are some currency systems that have non-standard denominations, meaning that it's not like ours where we have a 1 cent penny, 5 cent nickel, 10 cent dime, and or a 25-cent quarter. If I need to know how to make 59 cents, it's pretty obvious. You just pick the biggest one that you can without going over at each step, right? That's a greedy algorithm approach. But if I have a non-standard set of money, it's not going to work. In this case, if I have 1, 6, 9, and 10, that's not going to work. Because if I'm trying to make 15 cents with 1, 6, 9, and 10, and I try to do it greedily, first I'm going to take the 10, then I can't take the 6 or the 9, so I have to take 1, 1, 1, 1, 1, and then 1. No, I think that's okay. But anyway, you have to take 1, 10, and then 5 ones. But that turns out not to be the right approach here because that takes 6 coins, But I could have just taken 2 if I didn't do the greedy approach. If I had chosen the one that wasn't the max that I could take, if I had chosen the 9 and then chosen the 6, that would have only taken 2 coins to get me to 15. So this is an example where a greedy algorithm just does not work because you have to worry about special cases like this. In general, denominations of currency are not designed like this because this is kind of a weird design, but maybe they are. Ours happens not to be, so a greedy approach for finding changes is workable, but this is not workable. This because you have to worry about a non-greedy approach. And then I also have an example here where greedy choices aren't guaranteeing a global like optimal, right? So this is harder to like define. You just kind of have to know it when you see it. When you divide a problem into subproblems, a greedy algorithm won't always work because there might be a case where choosing the locally optimal solution of each subproblem forgets the bigger picture and actually makes you not consider a better solution. That's kind of hard to demonstrate, but you kind of have to know it when you see it. So another time that they do not work is when you have something that requires backtracking or recalculation. So a greedy algorithm is by design, you don't have to keep track of anything really. You just have to do the best possible thing at each step and then work towards a global solution. But some problems require that you consider a bunch of different possibilities. Like when we're doing graph algorithms, I can't just find the first cycle that I find and say that's definitely the longest cycle, right? Because that's not necessarily true. We have to find all of the cycles and see which one's the longest cycle. So a greedy algorithm wouldn't work for a problem like that. Because they don't consider the whole picture. They just consider what's the best at each point. So another time that they do not work is, this is kind of less common in competitive spaces, like competitive programming when the problem is more well-defined. But when problems require an exact, not approximate solution, meaning that I don't want to just find one that's kind of close to the best, I want to find provably the best, then a greedy algorithm is not going to be the right approach every time. Because, like I said, for some types of problems like the currency one, it does find the right approach, but that does not find the right approach if it's a different type of currency, right? So you just have to be careful when you're deciding whether or not to use a greedy algorithm. You have to decide if the problem nicely breaks down, and like the framework I talked about earlier, you have to make sure that the choice is indeed locally optimal and safe to perform. Make sure that when you decide what to do at each step, it's not going to ruin the entire solution. But there are some problems where it just isn't a nice way to break it up and do a greedy algorithm. So some common techniques that I go to when a greedy algorithm is not sufficient, like I'm getting the wrong answer or it's not fast enough or something like that, right? The biggest one is going to be dynamic programming. Dynamic programming is another type of problem, very similar to greedy algorithms where you break it down into subproblems, but dynamic programming similarly builds up a solution, but it considers many different alternatives rather than just a locally optimal solution. So without going too deep into dynamic programming, it is basically like greedy algorithms, but better because it considers the entire picture. Backtracking algorithms are going to be another time, or backtracking problems are going to be another time where greedy algorithms don't work, right? If you encounter a point where there's no longer a valid solution for you to do, you have to go back to the point where there was one and choose something that you didn't choose the first time. If I'm building up a solution and I reach a point where there's nowhere to go, I have to go back where there was a point to go and choose a different thing, right? So this backtracking thing comes up a lot in like puzzle games where you have to have like decision trees where you can either choose to do A or B. And then at the next thing, you can choose to do A, B, or C. You can do these different things at different steps. So like Sudoku, if I'm trying to fill in an entire puzzle, a greedy algorithm wouldn't work because I eventually would run into a problem where there's not an option to place anything anymore, which is when I would have to start backtracking, going to the last time and choosing something else, right? Solving Sudoku happens to be a very algorithmically complex problem because there's not really a nice way to do it, but if you're familiar with big O notation, I think it's O of 9 to the n squared. And then there's other problems that are called branch and bound problems. Yeah.
That on like backtracking,
Mhm.
is that sort of like depth for AI?
Yeah, similar. Yeah. Yeah, exactly. So, you use backtracking in depth first search. You go all the way down the branch and then you backtrack to the last time and then you go down the branch again, right? So you backtrack to the last branch to go down. So, yeah, that's exactly how depth first search works, is backtracking. So on the branch and bound problems, these are I don't think I've ever seen one of these in an actual competition because these tend to be problems that don't have an exact solution. These are more like try to get as close as possible to an optimal solution. And because of that, it's not easy to score a solution if you don't have an exact thing. Because in competitive programming, they really want to give you a yes or no answer. They don't want to give you a kind of right answer. They want to give you either full points or no points. So it doesn't really work for problems where you have to try to approximate something. So some implementation tips. Sorting. Both of the examples I went over, we had to sort it, right? Sorting is essential to a greedy algorithm because what you're doing is trying to choose a locally optimal, which usually will involve sorting of some kind. Heaps are a way to sort stuff. You'll probably learn about that in your data structures class, but heaps, depending on which heap you use, a min heap or a max heap will either guarantee that the root of the tree is the minimum or the maximum of the values. That's kind of out of the scope of what we can go over today, but I can talk about that at some point about heaps. I don't want to take over Tom's thunder too much about his data structures class, but basically an implementation tip that I have is just practice different greedy algorithm problems. I have a couple examples at the end if you want to practice on your own, but like with everything in this field, you pretty much just have to get a feel of it by doing it. There's not like a surefire way of do this thing, then do this thing, and you'll know exactly what to do. You kind of just have to practice a lot, and then you'll get a feel for it. So for a recap, greedy algorithms, they find a locally optimal solution for subproblems, hoping that this will lead to the globally optimal solution. And keyword there is hoping. We can't guarantee it. Like I said before, you kind of have to use your judgment to see if a greedy algorithm is going to be sufficient to give you the answer. It works well for problems that are conducive to breaking down into subproblems, where you can, like I said, guarantee that if I choose the best thing at this point, it is going to be the best thing overall. It doesn't work if it's not the case, right? If the locally optimal solution doesn't lead to a globally optimal answer, that does not work. So my advice for the competitions: know the theory on greedy algorithms, but also have a backup plan in your mind on something to switch to if the greedy algorithm turns out not to be sufficient. If it turns out to give you the wrong answer, or it turns out to be too slow, or anything like that, you kind of have to have a backup plan in your head of a different, more complicated algorithm to implement, because greedy algorithms are quick but not always right. And then I have a blog post up here that I read the other day that I thought would be really interesting for people to read. It's called The Greedy Guide: Essential Problems and Solutions for Competitive Programming. As you could guess by the title, it talks about greedy algorithms, specifically for competitive programming. If you just look up that title, it'll give you the blog I'm talking about. I think the guy has like 4 last names and I don't remember them, but yeah, his first name is Gary. I think it's on Gary Bricks, garysbricks.com or something. And like I said, I have some practice problems listed up here. So I have an easy one, a medium one, and a hard one. So the easy one is going to be minimum scalar product. Don't want to get too into that, but you can just go to Caddis, type in caddis.com/problems/ minimum scalar like I typed out here. That's called the problem ID, and you can end up getting that. And then watering grass, similarly, except you just type in grass. And then the hard one is called Magic Checkerboard. And when I say hard, I mean hard. Greedy algorithms, I kind of talked about it earlier. They tend to be only reserved for the easy questions, but on occasion, they will toss out a very hard question to give you, but the greedy algorithm is the right approach. And that happens to be the case for this caddis problem, a magic checkerboard. I would definitely encourage you to start with the easier medium ones because the magic checkerboard is quite complicated. I actually have yet to write a solution for that one, but I'm working on it. Does anybody have any questions about those? What time is it? Oh, 7 exactly. Okay. I was thinking I could go over the easy one here or the medium one even if you want me to, but it looks like we're out of time. So, yeah. Any questions about that? If not, you're free to go. Cool. Must have explained it really well. No questions. Thank you, everybody, for